Welcome to lecture 4 of electrical machines course. So again we'll continue the review of theory of electromagnetism. In the last class, in fact, we discussed the magnetic circuit analysis, how we can analyze the magnetic circuit similar to the electrical circuit, like considering the KVL in the electrical circuit. Here we can write the Kirchhoff's magnetomotive MMF law and Kirchhoff's current law as well. So all these things we have seen, and in this lecture let us solve some problems on magnetic circuit. Maybe 2 problems we'll consider in this lecture, and then we'll continue. So your first problem is there is an electromagnet of square cross section, okay, and has a tightly wound coil with 1500 turns. The inner and the outer radii of the magnetic core are 10 centimeter and the 12 centimeter respectively. So the length of the air gap, there is an air gap of 1 centimeter. If the current in the coil is 4 ampere and the relative permeability of the magnetic material is 1200, determine the flux density in the magnetic circuit. So this is your electromagnet, right? Already you have seen this structure, and the air gap is here, and the air gap is of 1 centimeter, right? 1 centimeter. And the current in the coil is here 4 ampere, and relative permeability is 1200. Please do it simultaneously. I'll show the solution as well. And you have to determine the flux density in the magnetic circuit. So flux density you have to find, okay. So now how to proceed in this? So the cross section of this toroid is square size, and the number of turns is 1500 here, n equal to 1500, okay. And the inner outer radii is given 12 centimeter, and outer radii is 12 centimeter, and the inner radius is 10 centimeter. So if we'll find the min perimeter, right? So min perimeter we can find using this formula, that is 2 pi r. Obviously L will become equal to 2 pi r, right? So this is 2 pi r will be equal to min radii will be 11 centimeters, so 2 pi 11, right? Okay, so now now let us see the solution. The solution is here. So if we'll find this length L, that is in the perimeter of this toroid, right? That is 2 pi into 11. And if we'll find, so we have 2 reluctances here in this magnetic flux path, right? So one is the reluctance offered by the material, that I'll say Rm, and other reluctance offered by the air, that is, let us Rg, okay. So if I want to find the Rm, then I need to find the length of the material around the circumference of this circle, right? So that I can find 2 pi into 11 minus 1. 1 centimeter is your air gap. So 2 pi 11 minus 1, that will give me around 68.12 centimeter. Okay, so that that is what I'm substituting here to find the reluctance of the material. So reluctance of the material, I can find it by the formula. Already we know the formula is L by mu A, right? So L is your 68.12 centimeter divided by the mu is 1200. This is your mu, 1200 into 4 pi 10 to the power minus 7. This is in fact mu naught, 4 pi 10 to the power minus 7, and mu naught into mu r, both that will give me mu, right? So that will the permeability of the material. And the area, obviously it is given, that is the square section, it is 4 centimeter square, okay. So the area is square has tightly wound the inner and outer. Okay, so the area is 4 centimeters square, so it is given maybe, right? So I can write it. Area is 4 centimeters square. So here it is given area, right? So now in order to find this reluctance offered by the air gap, so obviously I'll write the same formula. So L by 4 mu A, so that will give me a length is 1 centimeter and mu is given because air the relative permeability approximately 1, so therefore I can write the permeability of the air is 4 pi into 10 to the power minus 7. So that will give me the reluctance of 19.894 in 10 to the power 6. Okay, so now after finding this both the reluctances, I can add these both the reluctances in order to find the net reluctance offered to the flux path, that is Rm plus Rg. So if I add it, it will give me around 21.023 into 10 to the 6 ampere turn per Weber. Now from this expression I can find phi. The already we know phi equal to nothing but it is Ni, that is mmf by the reluctance. So total reluctance we know, right? And mmf is 1500 into 4 ampere. So that will give me the flux passing through this electromagnet, that is 285.4 not 2 into 10 to the power minus 6 Weber. And from this I can find the flux density in the material. So flux density in the ferromagnetic material and the flux density in the air will be different because the flux the MMF for both will be different. MMF will be phi is the reluctance will be different for both material and the air gap. So therefore the flux density will be different, right? So for flux density for the so therefore flux density will also be same. So Vm equal to Bg, that is nothing but phi by A. So phi is equal to 285.402 into 10 to the minus 6 by 4 into 10 to the minus 4. That will give me 7.714 Tesla. Okay, this is a simple problem. Now let us consider another problem. Here we assume that the flux density is in fact the permeability is not changing with the saturation of the core, because we're assuming that the core is the material, the magnetic material is working in the linear region, right? So it is operating at the linear region. That means without any saturation. That means the BH curve is linear here. We have assumed, right? Therefore, your permeability remains constant. Okay. And here in this example, we'll assume a nonlinear characteristic, magnetization characteristic. That is BH curve is nonlinear here. So if it is nonlinear, then the equation that implies that is B equal to mu H will be not linear. So therefore mu will not be constant in the magnetic material. So this equation will not be valid in this case because the magnetization curve is nonlinear. Okay. So now let us see this example. As already last class I have discussed all these things. So there is a magnetic circuit with its pertinent dimensions in the millimeters that is given here, right? Here the dimensions are given, the height, width, everything is given, and the thickness of the magnetization characteristic of the magnetic material is shown in the right side figure. This is your magnetization curve, which is the characteristic between the flux density and the magnetic field intensity, right? B and H. If the magnetic circuit has a uniform thickness, so that means the thickness of this core is 20 mm, right? That is the thickness, let us say T. And the flux density in the air gap is 1 Tesla. Here in the air gap, the flux density is 1 Tesla. Find the current in the 500 turn coil. So I need to find this current. So how I will proceed then? How to find the current in the coil? If I know the MMF produced by this coil, if I know the MMF, that is Ni by the coil, then I know the number of turns, so I can find the current, right? So therefore I need to find the MMF produced by this coil. So how I will find the MMF produced by the coil? So MMF, we know that is Ni is equal to MMF. So this is nothing but equal to H into L, right? So that is H is your magnetic field intensity into the length through which the flux is passing, right? So therefore length I know because I can find the mean length of the core. The mean length of core I can easily find from, because all the dimensions are given here. So I can find the mean length of this core, right? Of this magnetic path or magnetic circuit, whatever you say, right? So mean length is just in between, just in the middle of the core, that is the main length. We call it main length, right? So L I know, so I need to find H. So H we know is flux density by into area, right? But here this relationship will not work because the flux density only we know in the air gap, and we need to find the flux density here. And also this sorry, H is B into mu, right? Sorry, mu. So this will not work because the magnetization characteristic here is non-linear. It is not linear, right? So therefore this will not work. Okay. So now what we have to find? We have to find H. So H we can find from this magnetization curve if I know the flux density, right? So if I can calculate flux density at different point, like here at this point I can find the flux density, at this point I can find the flux density. So at different point, if I can find the flux density, I know the flux density in the air, it is given, right? 1 Tesla. So if I know accordingly, I can find the corresponding magnetic field intensity from this characteristic, right? Suppose I found the magnetic flux density of any section. Suppose let us say section BC, and BC is 0.75. Suppose then I can find corresponding to this the magnetic field intensity. This will give me the value of H for the section BC, right? HBC, I can represent this. Similarly, for each section, I can find the magnetic field intensity from this characteristic. And after finding this, I can multiply L, corresponding length of the section, different section, and add it. Then I'll find the net MMF, right? And after finding net MMF, I can find current I. So this is the procedure we'll follow, right? So now let us see. So the flux density is given in the air gap, that is the section AB, right? Let me erase all this. So section AB is given here, that is 1 Tesla flux density. And now I want to find this flux in the air gap. So how much flux will pass through it? That is nothing but 1 Tesla into area. Area I can find it, just all the dimensions are given, right? So after multiplying, I'll find, because the air gap is 2 centimeter, so I can multiply and find the area, and then I can, sorry, area is this, right? 6 into, so this is your flux density 1 Tesla, 6 into 20 into 10 to the minus 6. This is the area, right? So now after finding flux in the area, so this is the flux in the air gap. Now this flux will flow in the whole magnetic circuit, right? So that means because it is a series circuit, series magnetic circuit, so therefore the flux will remain same throughout the magnetic circuit in the air as well as in the material. So therefore the flux will remain same. We can see here. So we have different sections. We identified there are many sections A, B, B, C, C, D, D, E, F, and F, A. We can see here in this diagram we have many sections, right? So A, B, B, C, then C, D, then D, E, E, F, right? So these are the sections, and then F, F, A. So these are the sections. We need to find the H for these sections. So we know the flux rate, flux for all the sections will be same, that is 0.12 milliweber. And if I'll multiply the area, corresponding area with the flux, then I'll find the flux density in that particular section, right? So the cross-sectional area of each section I can find because the dimension is given. So like the cross-section, the section AB, for section AB, the cross-sectional area is given 120. It is already we know 1 Tesla. For air gap it was given. Similarly for BC, section BC, I can find the flux density by multiplying the cross-sectional area. That is also 1 Tesla, right? And after finding for each section the flux density, so for different section we found the flux density. Now after finding the flux density, now I'll proceed to find H. So H can be found from this magnetization curve, right? So like suppose for air, I want to find air gap, I want to find the H, that is the magnetic field intensity. Then I have to see 1 in the magnetization curve, and corresponding H will give me the uh, value, right? Okay. Sorry, for air it is given, right? For air we don't need to follow the magnetization curve because the magnetization curve is for the ferromagnetic material. So for air I can directly write H equal to B by mu. For air we know it is equal to mu naught. So just by substituting mu naught I can find H for air. So this is the formula applicable for air gap. And for other sections, I will follow the magnetization curve. Okay, like for section BC, the B is 1 Tesla. So for section BC, I can find here. So 1 Tesla is here, right? So now corresponding to this, if I'll make a projection to the H axis here, this value will give me the corresponding H value. So this will give me HAB, right? So HAB will be this much, 850, around 850 ampere turn per meter. Similarly, for all sections, I can find H, right? Corresponding to the calculated flux density, I'll find H. Then after calculating H for respective sections, then I'll multiply the medium length, sorry, the main length. After multiplying the main length, so the air gap length we know 2 centimeter, then the BC main length will be 56 centimeter, so 56 millimeter. So after multiplying, I'll find the MMF corresponding to each of the section. So we found the MMF corresponding to different sections, and then I'll add up all these MMFs, right? So that will give me H into, sorry, MMF is your H into L, that is MMF. So this is your net MMF, right? So this net MMF I found, this is your net MMF, that is Ni. Okay. So now the number of turns I know, I can find the current. So current will be 1863.75 by 500. 500 is the number of turns. So I found 3.73 ampere. Okay. I hope everybody understood this. Okay. Now next we'll move to self and mutual inductances. After finding this, we'll see if there are many coils, they are connected in series or parallel, how we'll find the self and mutual inductances, right? We'll see next. So now self and mutual inductance we'll discuss. So why it is important to find self and mutual inductance? Because we know in electrical machines for analysis we always need one equivalent circuit, because we cannot analyze directly this electrical machine. So therefore we need one equivalent circuit, electrical equivalent circuit, right? And these equivalent circuits are always represented through RLC parameters. Okay. So obviously C doesn't play more role in the electrical machines, but it plays important role in other part of the electrical circuits like transmission line and other elements. But we are not including all those in your electrical machines course. So here only we are worried about R and L. So your equivalent circuit will be consisting of resistance and inductances, right? And therefore it is very important to find out because this is a kind of circuit, different coils that are connected together in series or parallel. And after finding the inductances, mutual and self inductances, we can in fact write the equations, corresponding circuit equations, and we can analyze the circuit. And obviously I can, through that we can analyze the performance of the machine, electrical machines. Okay. So now let us see, here we have a simple coil, right? Simple coil, it's given. It is a toroid, it's having square shape. And we have number of turns here N, and a voltage source is connected which is injecting a current of I. And obviously through this current, when this current will flow through this coil, because of the, we know the, because of the Faraday's law, there will be an induced EMF in the coil because of the rate of change of the flux in the coil, because it is AC source, fluctuating AC source, right? So therefore, because of this, it will produce, because of the fluctuating flux, change in the rate of change of the flux will produce an EMF which is exactly opposing to the voltage which is in fact producing it, right? So therefore V and E are, they're opposite to each other. Therefore it is, you can see the representation, they're represented opposing to each other, right? So therefore I cannot put the negative sign here in the equation. So therefore I can straight away write E equal to N d phi by dt, right? Because I am representing here in the figure as, only I'll show the magnitude here, right? Representing it in the opposing fashion, right? So obviously the E will be equal to N d phi by dt, right? So the self-inductance, we know the according to the definition, the self-inductance are simply the inductance of a coil is defined as the ratio of a differential change in the flux linkages to the differential change in the current, right? So this is nothing but, obviously it is there. So this is nothing but will be rate of change of the flux linkage to this coil, right? So that is obviously N phi is the net flux linkage to the coil. So therefore I can write d of N d phi by di, right? So obviously N will be coming out, N is a constant. So N d phi by di. Okay, so this is the definition for self-inductance. Now I can write E with little adjustment. If I'll do some adjustment, I can write N d phi by di into di by dt. So here d phi by di, I know N d phi by di, I know it is nothing but equal to L. So I can write it as L di by dt. And also we know phi equal to Ni by reluctance, that is MMF, net MMF by reluctance. And just by substituting here in this equation phi, so what will happen then? It will lead to L equal to N square by reluctance, right? And 1 by reluctance is nothing but permeance. So permeance into N square. So L I can write in terms of constants, permeance into N square, or N square by reluctance. So in the magnetic circuit, reluctance is equivalent to the resistance in the electrical circuit, and permeance in the magnetic circuit is equivalent to the equivalent to the conductivity of the, sorry, equivalent to the Permeance is conductivity of the conductor in the electrical circuit, right? Okay. So now, or you can say conductance. Sorry, it is permeance is equivalent to the conductance, not conductivity exactly. It is equivalent to conductance in the electrical circuit. Okay. And reluctance is equivalent to resistance of the electrical circuit. Okay. So now self-inductance of a coil is, we can define it as in this way, as if the coil is having 1 Henry self-inductance, then if a change of current of 1 ampere is injected in this coil, that will produce a voltage of 1 volt. Okay. As per this definition, okay, LDI by, sorry, L is your 1 Henry and the voltage is equation is LDI by dt, right? So from this expression, this definition is there. So a 1 inductance of 1 Henry value of the coil will produce a 1 volt when we inject a current that is varying in the rate of 1 ampere per second. Okay. Now let us consider for this toroid, your phi will be equal to, obviously for the toroid we have shown previously that, not for this, the toroid we have seen that circular toroid we have seen in the last example also, and it is shown previously in the last class I have shown, and for that we have already derived the flux equation, and we found that the flux equation was mu ni by 2 pi h ln of b by a, right, for this toroid. Okay, and if we'll substitute this phi, and I will want to find the expression for L for this toroid, right? This toroid is like this. For this toroid, then L will be nd phi by di, and after taking the differentiation, I'll find mu by 2 pi n square h ln of b by a. So that will give me the inductance of this toroid, that is a circular toroid, right? Now if we'll find the equivalent circuit for this toroid, it will give me the resistance and inductance together, because this resistance will show the resistance of the coil, that is the coil around the toroid, right? And L is the inductance of the coil. So they both will be in series, and that is connected through a current source. So this will be the equivalent circuit for the toroid. Okay, so now we'll move to the mutual inductance. Already we have seen the self-inductance. So what is mutual inductance? Now if your circuit is like, there is an electromagnet which is having two coils, right? One coil is here which is connected to a voltage source, varying voltage source, and it is producing a varying flux. And we can see here the flux is passing through this core, this ferromagnetic material. And if we say that the portion of the flux produced by this coil, let us say phi 21, is linking to the coil 2, that is having number of turns n2, then what will happen? Then let us say the flux leakage here is phi 1L, that is the flux produced here is phi 1, and the leakage flux is phi 1L, and the portion which is confined to this core is also linking to the second coil, coil number 2, and let us say the flux value is phi 21, so I can write it as phi 1 is equal to phi 21 plus phi 1L. So this phi 1L is your leakage flux, right? So that is leaking to the air. Okay. So now I can write the equation. If I'll write E1 in terms of the self-inductance, let us say the self-inductance of the coil is L1. So I can write E1 equal to N1 d phi 1 by dt, which is phi 1 is the net flux produced by this coil, and the same flux is linking to this coil. So therefore I can say N1 d phi 1 by dt, that is equal to L1 di 1 by dt. I1 is the current flowing in this coil. So I can write it as L1 di 1 by dt, that is equal to also E1. And here L1 is the self inductance of the coil. Okay. And now if I'll find the voltage induced at the coil 2, so I can write it as E2 equal to N2 d phi 21 by dt, that is the flux produced by this coil, the portion of the flux produced by coil 1 which is linking to coil 2, that is phi 21. So N2 into d phi 2 by dt. N2 is the number of turns in the coil 2. And with little adjustment I can write N2 d phi 21 by di1 into di1 by dt. So I can write this as M21 di1 by dt. So M21 is nothing but that is equal to N2 into d phi 21 by di1. This is equal to M21. So this M21 is known as the mutual inductance. Okay. So M21 is nothing but N2 d phi 21 by di1. So this is nothing but the mutual inductance of coil 2 with respect to coil 1. So this is nothing but this is the change in the rate of change of flux, that is the portion of the flux which is linking to coil 2 which is produced by coil 1 with respect to the rate of change of current passing through coil 1, right? Okay. So now this is your M21. So if again I'll connect the source here in coil 2, here as shown in this figure, the source is connected to coil 2, and I want to find the mutual inductance of coil 1 with respect to coil 2. So in a similar way, if I'll proceed, I can write the equation of E2 and E1, that is induced EMF across the coil 2 and induced EMF across the coil 1. So induced EMF across coil 2 obviously L2 di2 by dt, and induced EMF across coil E1 will be M1 to di2 by dt. Similarly M12 is nothing but it will be N1 d phi 12 by di2. And here phi 12 is what? Phi 12 is the portion of the flux that is produced by coil 2 which is linking coil 1, right? That is phi 12. Okay. And because of this, the mutual inductance comes into M12, that is mutual inductance of coil 1 with respect to coil 2. Okay, now if we write phi 21, that is this is a fraction of the flux of phi 1, so I can write K1 phi 1, where K1 is defined as the fraction of the flux of coil 1 linking to coil 2. So obviously K1 will have a magnitude which is lying between 0 to 1, right? So 0, I can write 0, K1 less than 1. So it will always lie within 1. Similarly also K2, whereas K2, so phi 12 is nothing but equal to K2 phi 2, where K2 is obviously, it will also lie from 0 to 1. K2 determines the fraction of the flux of coil 2 linking coil 1. Then I can write the above equation. If I'll write one equation here by multiplying these mutual inductances M21 into M12. So by multiplying these expressions of M12 and M21 both, so M21 is the mutual inductance of coil 2 with respect to coil 1, and M12 is mutual inductance of coil 1 with respect to coil 2. So if I'll multiply both, the expression will become N1 N2 d phi 21 by di1 into d phi 12 by di2. So now if I can write this again, this multiplication as, because we know this flux is a fraction of this flux, I'll substitute here K1 phi 1 and here as K2 phi 2, right? So that will give me K1 K2 L1 L2. Okay. So now the product of the mutual inductances is nothing but equal to K1 K2 into L1 L2. So in a linear system, we expect that M12 equal to M21. If your magnetic material is linear. That means when it is operating in the linear region, unsaturated region, under that condition, M12 will become equal to M21, and that is, let us say, that is equal to M, where M is the mutual inductance of coils 1 and 2. So now substituting M, I can write M equal to M square equal to K1, K2, L1, L2. So M will be equal to square root of this K into L1, L2 square root. So K is nothing but square root of K1 and K2. K is nothing but square root of K1 and K2. So I can find the mutual inductance of this coil if it is operating in a linear region of the magnetization. That means with unsaturated condition, this coil is working, then your mutual inductance will be same and the value will be K into L1 L2 square root. So K is K1 K2 square root. Okay. So this is about self-inductance and mutual inductance. So the value of K obviously can have the value of K it will lie between 0 to 1, and it will have a value of 0 when both the coils are magnetically isolated coils. That means there is no magnetic coupling between these two coils, then K value will be 0. And it will be 1 when the magnetic coils are coupled very tightly. That means it is it is wound over one another. That means coil 1 is wound, and over that again the coil 2 is wound. Then we can say this is the tightly coupled coil. That leakage is very less, right? It can be neglected. So in order to minimize the leakage flux, the two coils are usually wound over each other. It is in fact the design of the transformer. In transformer we'll study how the windings are wound over each other in order to minimize the leakage flux. We'll discuss more about this. So when more than two coils are coupled together by a common magnetic circuit, each pair of the coils has a separate coupling coefficients. Okay, obviously it will be, and this is the equivalent circuit of that coil, of that two-winding coil. We can say two-winding coil, which is put in different limbs of this core, right? So that will in fact give this equivalent circuit for our analysis. So the equivalent circuit is R1, L1, R2, L2, and M is the mutual inductance. So R1 is the resistance of the coil 1, electrical resistance, and L1 is your inductance, self-inductance of the coil. R2 is your resistance of the coil, and L2 is the self-inductance of coil 2. M is the mutual inductance between coil 1 and coil 2. And this M is equal when this circuit is working under unsaturated condition. Okay, that means it is operating in the linear region of the magnetization curve, unsaturated region. So there is a small problem you can do also. This small problem, two identical 500-turn coils are wound on the same magnetic core as shown in the previous figure. A current changing at the rate of 2000 ampere per second in coil 1 induces a voltage 20 volt in coil 2. So from this we can see the current changing at the rate of 2000 ampere in coil 1 induces a voltage of 20 volt in coil 2. Okay, what is the mutual inductance of this arrangement? If the self inductance of the coil is 25 millihenry, what percentage of the flux set up by the coil 1 links coil 2? So this is your question to find the value of K. Okay, and also to find the mutual inductance, both we need to find. So how we'll proceed? The self-inductance is given 25 millihenry, which is equal for both the coils because both the coils are identical. So I can write L1 equal to L2 equal to 25 millihenry. Okay, and there is a rate of change of current that is 2000 ampere per second. That is in coil 1, Di1. I can say Di1 induces a voltage of 20 volt in coil 2. Okay, so that means E2 is 20 volt. So E2 I can write LDI 1 by, sorry, this is M. Let us see the solution. This is di by dt, right? So that M will become 20 by 2000, right? So obviously we know this, your E2 is equal to M di di1 by dt, right? Sorry, rate of change of flux di by dt. So M I can write as 20 by 2000. Okay, so this is very clear. So I can find M from this given fact. And then the self inductances are given. So L1 and L2 they are given. So I can find from this equation the K value, right? So the K will be nothing but M by L. So it is L1, L2 is given 25 millihenry. So K is 0.01 by 0.025, that is 0.4. That means with this arrangement, 40% of the flux produced by coil 1 links coil 2. Okay, this is your K value. K value is 0.4. Okay, so now let us see the magnetically coupled coils. So there are two and more magnetically coupled coils that can be connected in series or in parallel. When they are connected in series parallel, so what happens? How will calculate the net inductance? Let us see. So the effective inductance of the magnetically coupled coils depends not only upon the orientation of the coil but also the direction of the flux produced by each coil. A two-winding transformer, auto transformer, and induction motor are example of such magnetically coupled coils. The coils are connected in sometime in series, sometime in parallel. So we'll see. Unless we know this analysis, we cannot also properly do in the masons. These are the general analysis, and through this we can also analyze different masons like transformers, auto transformers, right? So let us first consider the series connection. So if I will have two coils, they are connected in series, okay, and having self inductance L1 for the first coil and L2 for the second coil, and the mutual inductance between these two coils is M, and they're in the condition that the magnetic flux is aiding each other. That means when this voltage source is connected to these coils connected in series, so when the current passes through these coils, they will produce the voltage in such a manner that voltages will be additive in nature. They will not oppose each other, right? So that is why the dot convention is mentioned. This dot convention indicates that when the flux is produced in such a direction that the polarity of the voltage will be exactly at the dot points. Okay, so that is the dot convention, and here we can see the voltages are in additive in nature, right? That therefore we call it the fluxes are aiding each other. Okay, so under this condition, under the condition of aiding each other, flux aiding each other, so we can write the voltage equations across the inductances. So V1 I can write for coil 1 equal to L1 di by dt plus M di by dt, right? The same current is flowing. So the L1 di by dt is this voltage, this portion voltage is in fact because of the self inductance of the coil, and this voltage is in fact because of the mutual inductance and current flowing in the second coil. Okay, M di by dt. Similarly, I can write V2 also, that is L2 di by dt, that is the voltage produced because of the self inductance in the coil 2, and the voltage produced because of the mutual inductance in coil in between these two coils. So V2 also L2 di by dt plus M di by dt. So now if I'll add these voltages, I will find the net voltage. So net voltage will be V equal to V1 plus V2, that is equal to L1 plus L2 plus 2M into di by dt. Okay. So now this is called the series aiding, because under the series, when the coils are connected in series and the flux are aiding to each other, so under that condition we found the net inductance as it is equal to L1 plus L2 plus 2M, right? This is your net inductance. Now similarly, if we'll have a circuit where the coils are connected in opposing fashion, that means the fluxes are opposing to each other, right? That means you can see here the dot convention, right? The fluxes are produced in such a way that here the fluxes are opposing to each other, right? You can see here the voltage terminal, the plus terminal is not at the dotted terminal, right? If it is at the dotted terminal, then it might be a correct in the aiding fashion, right? So now for the opposing condition, the flux, when the fluxes are opposing to each other, we can write similarly, we can find the expression for V1 V2, and if we'll write the net voltage equation, it will give the equation like this, and here it will become minus 2M, right? So this will become L equal to L1 plus L2 minus 2M. Okay, because here the sign will become negative. For V1 it will become minus mdi by dt, V2 it will become minus mdi by dt, because the flux, mutual flux is opposing. So your net voltage will here it will become minus 2M. Okay, so therefore your net inductance will become L1 plus L2 minus 2M. Similarly, it can be derived, right? Now, if these coils are connected in parallel, then what will be the case? Suppose this is the circuit where the coils, two coils having inductances L1 and L2, they're connected in parallel, and the mutual inductance between these two is M. So under that condition, if we see the voltage source is connected here and the net current passing through is I, and the current passing through inductance 1 is I1 and inductance 2 is I2. Okay, so now if we'll write the equation for current, so your current will be I1 plus I2, and if I'll take the derivative of this, it will be di by dt, that is equal to di1 by dt plus di2 by dt. And this is this M here, the connection is in such a way the fluxes are aiding to each other, right? As we have seen the dot convention here, the current is entering to the dot points, and the M is here, the mutual inductance. When we write the equation in the voltage form, it will be in the plus form, right? Because the flux produced because of each other is aiding to each other, right? So here we can write the voltage equation. I'll write the voltage equation V with the loop under this loop. So considering inductance 1 for this loop, right? So if we'll write, so V will be equal to L1 di1 by dt plus M di2 by dt, because they are in the aiding each other, the flux is aiding each other, so therefore I'll write plus M di2 by dt. Similarly, again, if I'll substitute here in case of di1 by dt from this equation, here di1 by dt will be di by dt minus di2 by dt. By substituting this here in this equation, it will give me the voltage equation L1 di by dt minus L1 minus M di2 by dt. Again, if we'll write the voltage equation V considering the second loop, this loop, right? So then V will be equal to L2 di2 by dt plus M di1 by dt. And again, by substituting di1 by dt here in this equation, I can find the voltage equation will be M di by dt plus L2 minus M di2 by dt. Now these both equations are applicable to this circuit, so therefore the voltage equations will be same. So now by equating these two equations, if I equate these two equations, from these two equations I can find di by dt just by some manipulation, just by adjustment. I'll find di by dt will be equal to L1 plus L2 minus 2m by L1 minus m, that into di2 by dt. Just eliminating di by dt, I can find this equation. And also if I will take the net equivalent inductance of this, if I'll take the net equivalent inductance of these two inductances as L, and I can represent like this here. This is your net inductance L. That is the net inductance of this parallel combination of L1, L2, let us say L. Then I can write the voltage equation in this way, V equal to L di by dt. Okay. So now again substituting here the d, again by equating these two equations, this equation and this equation, because these are the same voltage equation. So by equating I can eliminate di by dt. So di by dt will be equal to L1 minus m minus L by L1 di2 by dt. Negative sign is there, sign will be there. Just by equating both these equations you will find, and eliminating di by dt, you will find this expression. Okay. And now we have two expressions of di by dt, right? So again by equating these two expressions of di by dt, I will find the value of L, that is the equivalent inductance of these two parallel combination of L1 and L2. So just by eliminating L from these two equations, equating these two equations and eliminating L, I will find L1 L2 minus m square by L1 plus L2 minus 2m. So this expression is applicable for the condition when the flux is adding to each other. Okay, flux is adding to each other. So under that condition, L, the equivalent inductance, is nothing but equal to L1 L2 minus m square by L1 plus L2 minus 2m. So this is for parallel adding circuit, right? For series adding circuit, we found equivalent inductance as L1 plus L2 plus 2m, right? This is for series adding circuit. Similarly, for parallel opposing circuit, if we'll again write the equations and finally eliminate L and find the expression for L, we'll find again L1 plus L2, sorry, L1 L2 minus m square by L1 plus L2 plus 2m. So this will be expression, and this is as a home task, you can do this. Okay, please do this. And also, if possible, you can send me, or you can send me the email through email, or you can submit through, or else I'll post an assignment for this. You can do it and send it to me back. Okay, this is a very simple, you can derive it. Okay, so okay, so now time is going to over within 5 minutes. It is difficult to finish this magnetic losses. Maybe we'll cover in the next class. So we'll discuss this magnetic losses in the next class. Okay, we'll keep it for next class because we may not finish this. This is a little bit, it'll take time. So we'll discuss this magnetic losses in the next class. So now we can, we'll stop here and we can, okay, thank you very much.